So the considered equation of the plastic instability can also be written in terms of engineering strain, which is E. That can be written as the L minus L naught divided by L naught. So if we write the equation of d sigma by d epsilon equals to d sigma by dE into dE by d epsilon, that is equal to d sigma by dE. So this term, if we write it, dL by L naught dL by L, that is written as the d sigma by d E L by L naught, means the d sigma by d E 1 plus E. So the slope d sigma by d, this is slope of the stress strain curve, can be written as sigma by 1 plus E. So what is the meaning of this equation? So if this is true stress curve between true stress sigma and epsilon, and this is the curve. So if we draw a tangent at the negative -1 engineering true strain a point, so if we that will touch the, that will intersect the curve sigma versus epsilon curve at the maximum load. So this maximum load is called the ultimate tensile strength of the metal, corresponding to the strain of -1, and the strain related to this will be uniform strain. So the fracture in ductile metals will happen with the sequential process of means generation of voids and the fracture, final fracture. So you study the final fracture behavior. Means this is the metal and necking is start from at this position. So due to necking, triaxial stress state generates at the necking region. This is the loading direction. So with the deformation seed, small voids will start to form at the region. At the second phase, particles or oxide inclusions means voids or cavities. And after some point, when the voids and cavities will elongate and coalesce with other voids, means this is the coalescence, that will lead to a formation of crack. So first is the void or cavities nucleation. Then the coalescence, and that lead to the central crack. As the crack will start to propagate along the 45-degree angle because of the shear stress generation at the neck in this necking region. So this will start to propagate and form a large void, large crack that will lead to the final fracture of a cup cone type. This is looking like a cup and cone because of this region, means so void formation can happen at inclusions, second phase particles, and oxide particles. And also the grain boundary triple points. So the fracture will also generate at the local shear bands, means the shearing is happening at the 45-degree angle from the tensile loading direction, and the at this loading direction the voids starts to form first. So the initial generation of the voids will start from these shear band lines, and then the void coalescence will occur by the elongation of voids that bridges the material between these voids. So this void nucleation can be was is observed by a in situ tensile deformation in situ tensile test. And the elongated voids can be easily seen in a scanning electron microscope. So by the scanning electron microscopy, we can confirm that the voids elongate and then coalesce, that lead to cup and cone fracture by SEM. So the two modes of nucleation of crack. So this is the fracture behavior of a ductile metal. Now we will come to the fracture behavior in discontinuously reinforced metal matrix composites. So the generation of voids and crack nucleation happens in two stages, means two modes. Of crack nucleation. First is the particle cracking. And second is the interface decohesion. So which modes occur first depends on the particle size and the interfacial bonding. Particle size and interface bonding strength. So the particle crack. So with the small size of particles, reinforcement particles, with small size of reinforcement particles, the particles will crack with the deformation. Particle cracks, and with increasing size of particles, the increasing size mode will change from cracking to decohesion. So this cracking and decohesion behavior can also be seen in a scanning electron microscope. and the ductility of discontinuously reinforced metal matrix composites depends on matrix parameter. Like the ductility of discontinuous reinforced MMCs depends on matrix parameter. First is the void nucleation rate at the reinforcing phase. At the reinforcing phase, with suppression of strain relieving mechanism. Means as the void nucleation rate changes, the strain relief mechanism will also subjected to decrease, and that will decide the ductility of the discontinuously reinforced metal matrix composites. So the ductility of DRMMCs will decrease with increasing particle size and volume fraction. And ductility also decreases with as the void nucleation rate increases. So how the void coalescence happens in the matrix? As the matrix will start to deform by shear failure, means this is the voids creating, and if the matrix will fail between these two particles, so the shear failure will elongate the voids and void coalescence happens. So the void height will be decided by the intervoid spacing. Means if the intervoid spacing is large, so the void height will be less, final void height will be less, and if the intervoid spacing is less, so it will lead to the increased void height. So in the ductile, if there is a ductile matrix, discontinuously reinforced metal matrix composite. So ductile matrix will lead to the particle cracking and that lead extensive void growth along the loading direction. But there will be no lateral growth of the voids. Means only the void will grow along the loading direction in the there will be ductile matrix. And no lateral growth. This leads to the constraining effect of well bonded particles. Means there is no cohesion and particles are cracking during the deformation. So a constraint will be there on the matrix deformation. On matrix deformation is because of the well bonded particle cracking, the matrix deformation will be constrained. And the void nucleation by particle cracking leads means there will be very high ductility. The particles are bonded with the matrix strongly and the ductility will be high. In this this continuous reinforced matrix, ductility and toughness both. And if there are the stronger matrix, means ductility is low, that will lead to lateral growth and decohesion of particles. There will be lateral growth and no constraining effect occurring on the matrix. Then this lead to the less elongation before fracture. Means low ductility. So the void nucleation and constraint to plastic flow will get reduced. So the fracture surface of composite materials can be can be identified as the simple features in ductile matrix. Means for the ductile matrix there will be voids and dimples, and matrix necking to a knife edge. Means there will be a growth in deformation with the shear band, and due to the shear band along deformation, voids will grow and propagate, lead to a knife edge at the interface, at the edges of the sample material, to a knife edge between particles. And there will be a serpentine type of glide happening on the dimples. That indicate shear coalescence mechanism. Coalescence mechanism. And if the matrix is brittle matrix, there will be more complicated fracture surface. Matrix surface, and there will be voids, less voids, and reduction in voids, void size associated with particles. So this is the fracture behavior in the composite. Now we will study the fatigue behavior in the composite materials. So what is the fatigue in materials? So fatigue happens because of the cyclic loading and unloading condition at a dynamic rate. So fatigue is generally defined as the failure in dynamic or fluctuating loading. So due to the dynamic or fluctuating loading, a stress cycle will exist during the deformation process, and stress cycle can be defined in various types of cycles. First is the completely reversed stress cycle. Reverse stress. So the graph can be of the completely reversed stress cycle can be depicted by this. So this is 0, this is the number of cycles, and this is stress sigma. So this can be written as the sigma max, maximum stress, and this is sigma minimum stress. So the difference between this can be written as the stress range, sigma r. So the sigma r can be written as the sigma max minus sigma minimum. This is the range of stress. The minimum stress can be written as mean stress, sigma max plus sigma minimum divided by 2. And alternating stress, sigma A can be written as the sigma max minus sigma minimum divided by 2. And for this completely reverse cycle, the mean where sigma max equals to sigma minimum, when the sigma mean stress will be 0. This is for the completely reversed cycle. And when there will be a fluctuating load, means there will be no cyclic behavior. Like in this condition, the stress ratio in both condition can be written as the sigma minimum by sigma max. And there is also one more term which is called the amplitude ratio. So can be written as the capital A means sigma A by sigma m. This also can be written in terms of stress ratio. Which is 1 minus r divided 1 plus r. So these are the two modes of cyclic loading. One is completely reversed and second is the very fluctuating load. So in the information we get from the fatigue testing is the fatigue limit or endurance limit. So if we draw a curve between stress and number of cycles, a curve will follow a path like this. Means for a low stress at which the material will not fail for an infinite number of cycles. So this stress value is called can be written as the fatigue limit of the material or endurance limit. So the fatigue limit and endurance limit can also be in the case of steel and titanium, while for other metals like aluminium and magnesium, the stress will continue to decrease with increasing the number of cycles. When there will be no fixed point that can be written as the fatigue limit. So for this condition, a stress value corresponding to 10 raised to power 8 cycles is written as the fatigue strength of material. Means when material can be loaded for 10 raised to power 8 cycles without failure, then that strength will be the fatigue strength of for aluminium and magnesium alloys. So generally the data is collected in completely reverse cycle. Means only the experimental data is collected for the completely reverse cycle testings. And the curve shown in this slide is written as the SN curves. Means stress versus number of cycles curve. So for SN curve, the stress value can be written by an equation which is N sigma A P equals to C. This is constant. This equation is generally known as the Baskin equation. And so there will be two types of fatigue failure. One is the high cycle fatigue and one second is the low cycle fatigue. Means high cycle fatigue the number of cycles are greater than 10 raised to power 5 cycles, And for low cycle fatigue, the number of cycles will be less than 10 to the power 5 cycles. So for high cycle fatigue, the Baskin equation works. So during the testing, the specimens are subjected to a definite stress level. So the stress level starts from the 2/3 of tensile strength of the material which is being tested. So the 2/3 of tensile strength stress is applied to the specimen, and the number of cycles are counted. Then the specimens are loaded with decreasing load from the first loading value up to which the final up to which the cycles when the till the point where endurance limit is not achieved. So in fatigue testing, the sample is subjected to high stress first, then stress is decreased, for subsequent samples. To achieve endurance limit. So if we see a stress loading condition, and where the stress ratio is -1, where the sigma mean stress is 0, so this is the ideal condition. But practically, stress cycle may not completely reversed. Means practically sigma minimum is not 0. So for further analysis, if we draw a stress between maximum stress and log scale of number of cycles, capital N. So for a R, for a stress ratio value 0.3, the curve will look like this. If the stress ratio is decreased, the curve will also follow this path. Means for R equals to the 0, this curve will follow this path. For R equals to -0.1, and this curve is for R equals to -1. So as the stress ratio increases is greater than 0, means if R is positive, fatigue that lead to the increase of fatigue limit. Means if stress ratio is positive and greater than 0, that means the material can sustain the infinite number of cycles for a higher stress level. And In the second for the second condition, if stress is, so this is for sigma max and this is for sigma a, means alternating stress is plotted versus the cycles of failure. So curve will follow for different types of mean stress. So this is for sigma m1, this is for sigma m2, sigma m3, sigma m4. So the sigma 4 mean stress is greater than the all stress. Sigma 1 is greater than sigma 1 is, sigma 2 is greater than sigma 1, that is sigma 3 is greater than. If this condition it follows, it depicts that this condition represents as sigma becomes more positive, the allowable alternating stress decreases. Now this is the sigma 1, sigma m1, sigma m2, sigma m3, and this is for sigma m4. So sigma 4 is highest. So when the sigma m becomes more positive, the allowable alternating stress decreases. Means the alteration of the stress cycle will get reduced. Means allowable alternating stress is decreasing. So for each mean stress, there is a stress range sigma max minus sigma minimum. So if a curve is drawn between the maximum and minimum stress in tension or compression, this is in tension and this is compression. Stress, this is the stress range and this is sigma minimum and this is sigma maximum. So curve will follow like this, a line will follow. For compression will be this. So the angle between stress range and the number of cycles, so this is not number of cycles, this is mean stress. Angle between this is 45. So the difference between this can be written as the sigma alternating stress, and difference between these 2 points can be written as sigma r. Means this is sigma max and this line is for sigma minimum. And this point will represents the sigma u, means ultimate tensile strength. So as mean stress increases, the range of stress decreases, and at UTS the sigma r will be 0. So from this phenomena we can say that the high cycle fatigue is stress control. And now we will study the low cycle fatigue behavior. So the low cycle fatigue behavior is generally studied at very high stress, means because the number of cycles is less and stress level is high. So this condition can be achieved in thermal conditions where large thermal stresses exist. So thermal stress can lead to high stresses and low cycle fatigue. So in this condition, generally the cyclic strain failure happens, means the material fails because of the cyclic strain, cyclic deformation process. Means it is strain controlled. Means when the strain is controlled, so if a curve is drawn, stress strain curve is drawn, say stress strain. So when a material is loaded and unloaded up to a compression point, so this will follow this path, and if the unloading is done, so then this will follow this path, 0 OA and this B. So the strain is fixed in this condition. So this range is the delta epsilon. So this can be written as the delta epsilon by 2 and delta epsilon by 2, and this epsilon 2 is also written as, so this part can be written as the elastic strain and this part is written as the plastic strain. So this behavior of material and strain control test is represented by a Borschinger effect. Means this is the Borschinger effect. Means when the material is unloaded and loaded in compression, so the yield strength in compression is low. When it is subjected to further tensile loading, then the yield stress will achieve the initial point, yield stress point. So the total strain in this condition, delta ET, can be written as the elastic strain and the plastic strain. So with the cyclic loading and unloading conditions during deformation process, a state will reach where a stable shear strain stable stress strain loops will develop. So for a cyclic loading condition, the curve will follow this path. So due to the depending on the different materials, there will with the cyclic loading and unloading, one material can soften and one material can harden. Means there can be cyclic softening or cyclic hardening. So due to during deformation process, as the deformation proceeds, a stability in the deformation behavior is achieved. Means and the stress strain loop will also achieve a stable region. So if we match the maximum points and lower points for the stable loops, then this will follow this path. So this curve is this curve can be written as the cyclic sigma epsilon curve. Sigma epsilon curve, and one more curve can be achieved, so which has the less stress levels. This is monotonic. Monotonic sigma epsilon curve in the low cycle fatigue conditions. So the change in stress can be written for the low cycle fatigue condition as the K prime delta plastic strain prime and the plastic strain. So for this equation, the N prime is written as the cyclic strain hardening exponent. And K prime is written as the cyclic strain coefficient, strength coefficient. So when a curve is drawn for the plastic strain to failure, plastic strain range and cycles to failure, then a straight line is achieved, and the equation for this straight line can be written as the EF dash 2n power c. This equation is known as the Coffin-Manson equation for low cycle fatigue. And Coffin-Manson relation. So here delta EP by 2 is written as the plastic strain amplitude and 2n is the number of strain reversals. To failure. So one cycle means 2 reversal, and EF dash is written as the fatigue ductility coefficient. So this is the both conditions, means the high cycle fatigue, which is the stress controlled, and low cycle fatigue is the strain controlled. Now we'll study the fatigue crack propagation and growth. So the crack propagation and fatigue crack propagation and growth will happen in different steps. First is the crack initiation at surface. Second step is slip band crack growth. Third is the crack growth, and fourth is ultimate fracture. So what is meant by the second step means slip band crack growth. Means slip band crack growth will occur at the slip band. Means the slip band is along the specific crystal plane and direction. So first is the crack will initiate at surface, that will propagate initially at the crystal plane and slip plane direction, and on the slip plane, that will further grow with the transgranular mode, deviating from the slip plane and direction. So the fatigue crack is generally transgranular. So the slip generation of crack at surface is happens due to the uh, formation of slip band extrusions and intrusions. So when the slip occurs in a material, the material at microscopic level will microscopic or will show the slip bands in this manner if because of the shearing of planes. This is in the static deformation. This is static deformation contour. But in the fatigue deformation, there is loading, the changing of the loading direction, means one is the tensile loading and second is time is the compression loading. So due to the changing of loading direction, the slip band will form the intrusions or extrusions due to the back and forth movement of slip planes. So if the structure will form like this, this is called the intrusion leading to a crack. Notch intrusion, or this can be represented by a intrusion or notch due to the back and forth movement. If the condition is different, a protrusion or extrusion can also form in this behavior. So this is the extrusion of slip bands or ridge formation due to the cyclic loading and unloading. So with the slip band crack growth, the deepening of the initial crack on planes of high shear stress, means for the slip band crack growth, happens on high stress planes, high shear stress planes. Leading to deepening of crack. So this is the stage 1 crack. Second, stage 2 growth of crack. Stage 2 crack growth, which happens on the planes of high tensile stress. So in the stage 1 crack growth, the crack grow on the high shear stress planes, while for the stage 2 crack growth, the plane is high tensile stress and crack growth happens on this. So for the stage 1 cracking, there will be no feature, but for stage 2 cracks, striations will develop. On the fracture surface. that is of ripple form. Striations are generally of ripple form, and that can be seen as these lines. So each striation represents position of crack front. Crack front associated with that is normal to the largest tensile stress. Means there will be a plane normal to this where high tensile stress exists, and this striation will develop normal to this, means perpendicular to this high tensile stress plane. So due to the different cyclic loading, the crack blunting and resharpening happens because of change of loading condition, loading direction, change in loading direction. So for the crack growth, equation can be written between the number of cycles and the crack length. dA by dN means the change in crack length with the change in cycles. That is written as the A sigma A P A Q, A power Q. So A is the crack length, sigma is the alternating stress, A is a constant, and P varies from the 2 to 4 and Q varies from 0.2 to 2. So when Q is 1, so this dA by dN can be written as the A sigma A P. A1 epsilon 1 P power P. So for the progression in crack with the increasing number of cycle depends on the fracture toughness values of the material. So that can be written as the delta K. K is the change in stress intensity factor. So delta K is written as the K max minus K minimum, and K is the stress intensity factor. And the K can be written as the sigma root pi A. A is the crack length for it. So delta K can be written as the sigma max minus sigma minimum square root of pi A, and this term can be written as the sigma R stress range. So if a curve is drawn between the crack growth and the change in stress intensity factor. This is the crack growth and this is delta K. So a sinusoidal curve will form like this, which has the three types of stages. So this is the stage 1, and this is the stage 2 of the crack growth, and this is the stage 3rd. So the value corresponding to the stage 1 end is written as the threshold stress intensity factor, for which no cracks will propagate for infinite number of cycles, leading to a almost curved line in stage 2 crack growth. And after crossing the stage 2 crack growth condition, the fracture will happen rapidly. Means this point is the rapid fracture. Delta KH. So delta KH is the threshold for non-propagating crack. For the stage 2 crack growth, dA by dN can be written as C delta K power M. This equation is called the Paris law. And in the stage 3rd, rapid crack growth happens. Means the K value, K max reaches Kc. Means Kc is the fracture toughness of the material. Means after reaching this point, the material will rapidly fail. So for this condition, stage 2, the R stress ratio can be written as the K minimum by K max. That can also be written as the sigma minimum by sigma max. And the crack growth equation can be written as C delta K power M divided by 1 minus R Kc minus delta K. So the effect of R is less in stage 2 compared to first and third stages. So this is how the fatigue behavior of in aluminum alloys is explained. So now we will discuss assignment questions. So the in the equation 1, in the question 1, it is asked that which of the following statement is correct regarding metal matrix composites. So first statement says there is load distribution to the adjacent fibers before a particular fiber fracture. Second option says sequential fracture of fiber depends on coupling between fiber and matrix. This is correct. And the third option says if there is no coupling, the composite behaves like a bundle of fibers. So in this equation, all three statements are correct. Means there will be a load distribution to the adjacent fiber before a particular fiber fracture from the fiber to matrix. So all three statements are correct. Second question says which of the following statement is correct? Matrix yielding in brittle matrix material leads to stress relaxation. Second option says in a ductile matrix fibers can fracture before the global yield of matrix. This is correct. Third option says matrix yielding in ductile matrix material leads to blunting effect on the crack tip, preventing the crack from propagating to the adjacent fibers. So this is also correct. First option which says the matrix yielding in brittle matrix material leads to stress relaxation. No. In brittle matrix material, the stress relaxation happens because of the debonding of the fiber and matrix. So first option is incorrect. So the right option is C. Third option says in discontinuous reinforced metal matrix composites, the mode of void nucleation changes from particle cracking to decohesion with increase in particle size. Decrease in particle size does not depend on particle size. Void nucleation does not occur in DRMMCs. So the last option is incorrect. Void nucleation happens in discontinuous reinforced metal matrix composites. It depends on the particle size, and the void nucleation changes from particle cracking to decohesion with increase in particle size. So the first option is correct. Next question says which of the following statements are correct about the growth of a large size crack under a tensile load in the fiber direction. So first statement says there is a failure in both fiber and matrix. This is correct. The second option says if interface bonding of fiber and matrix is weak, then crack front is non-planar. This is also correct. So the both first and second option is correct. In next question says statement 1, for brittle matrices, failure of a single fiber does not propagate through the entire composite. No, it will propagate through the. For brittle matrices, the failure will propagate through the entire composite. So this is wrong. Weak interface bonding does not relax the fiber in the brittle matrix and leads to rapid crack growth. So this is also correct. Means the weak interface bonding relaxes the stress in the fiber from the brittle matrix debonding. So both statements are false. Means correct option is C. Next question says in ductile materials, the plastic deformation before fracture is much larger than the elastic deformation. Means in ductile materials, a large uniform or elastic strain, plastic strain is generally reported in ductile materials. So the third option is correct. In the seventh question, which of the following statement is true regarding discontinuously reinforced metal matrix composites with ductile matrix? So particle cracking is observed, void growth in the loading direction, void growth in both loading and lateral direction of the applied load. So only the void growth in the both loading and lateral direction of the applied load, not in the loading direction. This is wrong. So first and third option is correct. So right option is D. No, right option is C. Means void growth in the loading direction. This is correct. Yeah, means in the ductile matrix only the crack growth, void growth in the loading direction, and there will be hardly any lateral growth direction that leads to the increase in uh, elongation before fracture. So first and second option is correct. In the eighth question, fracture surface of discontinuously reinforced metal matrix composite with ductile matrix shows simple features like voids and dimples. Yes. Matrix necking to a knife edge between particles and serpentine glide on the dimples. So all three options are correct for the fracture surface in DRMMCs. Next question is, considering the following statement regarding the tensile behavior of highly ductile materials. First option is, they will continue to neck down to an infinitesimally thin edge or a point and thus fail. Yes, this is correct. The cross section at the neck remains the same till fracture. No, cross section changes. The cracks are found to nucleate at brittle particles such as oxide inclusions. Yes, because the void generates at the second phase particles oxide inclusions. So the third option is correct. So first and third means correct option is D. In the last question it is asked, pick the correct sequence of events in a cup and cone fracture. So first in this sequence, necking happens that lead to small cavity formation, then coalescence of cavities to form a crack, then crack propagation and shear fracture at a 45-degree angle relative to the tensile direction. So the correct option will follow the B option, is the B. So we will end the today's lecture. You can ask any doubt in the discussion forum also. Thank you. Okay, so good evening all. Today I will start the week 11 lecture review in the problem solving session. So in the week 10 lectures we studied about the different mechanisms of fiber and matrix interaction and the strengthening mechanism in the metal matrix composites. Today we will discuss about the fracture behavior of the fracture behavior of the metal matrix composites in continuous reinforced and discontinuous reinforced systems. So let's start. So the fracture behavior of MMCs. It says that the ultimate tensile strength of composite is insensitive to matrix behavior for a ductile matrix. But for the brittle matrix, the ultimate tensile strength just depends on the ultimate tensile strength of the reinforcement. So generally the matrix is known for its ductile behavior. And the mainly are the yielding and fracture behavior of composites we will is the main topic. So as we know, the matrix is generally is the ductile, and the fracture of the composite also depends on the fiber and matrix interfacial bonding. Means the fiber interfacial bonding decides the final behavior of the metal matrix composites. Means it will be ductile or brittle. So let's start the ductile matrix. Let's start with the ductile matrix. So in the ductile matrix, fibers can fracture before the global yield of the matrix, and crack will propagate along composite means the fibers which are very brittle in nature, these are fibers aligned, means continuous fibers. So they can fracture before the yielding starts in the matrix. And once the yielding of matrix starts, that leads to stress relaxation and blunt the crack. Means as the fiber fracture, the crack will propagate from the fracture from the fiber to the matrix region. So because of the yielding, the crack front gets blunt because of the plastic deformation near the crack front. And it also leads the matrix yielding also leads to stress relaxation. Means as the composite is subjected to a tensile load, so after the fracture of fibers, the stress will propagate through the matrix. So crack will propagate through the matrix with increasing the stress, and the stress can be released by the yielding of matrix. That's why the matrix is helpful in preventing the crack in composites when it's soft and ductile. And for brittle matrix, failure of a single fiber may propagate through the entire composite. Means the crack will propagate from the fiber to entire matrix. So the crack propagation will be very fast in this brittle matrix composite, and it will look like this. Like these are the aligned fibers. So the crack will be shown like this. So it will propagate through the composite section. So how to relax the stress in this condition when the matrix is brittle? So if the bonding at interface of matrix and fiber is can be decreased, means if the bonding strength between the matrix and fiber can be decreased by some region, then the stress can be relaxed. Means if so in this case, the fiber can easily propagate from the fiber to the matrix. So if interfacial bonding decreases at the surface, means this is fiber and this is matrix. So when this will if the matrix and fiber will separate, so due to the creation of surface, the stress can be relaxed. Stress concentration can be relieved. And the catastrophic failure can be prevented. And due to this, the loading direction also, the dependence on the loading direction of for fracture behavior of on the loading direction can also results in the anisotropy in mechanical properties. Means if the crack will propagate from this, so this will have the another strength, and if it will propagate perpendicular to the loading direction, then the case will be different. So the brittle matrix also result in anisotropy of properties in composite. So interface debonding can prevent the fracture in brittle matrix composite. Interface debonding means this is fiber and this is matrix. So the crack is this. If the interface debonding occurs, so that will release the stresses and prevent fracture. And if the single fiber fracture means if there is a if in the matrix single fiber is present, means only fracture is in the single fiber, so the load distribution in this condition is needed before the fiber fracture. And this also depends on the degree of coupling between fibers and matrix. Means how the single fiber fracture, it depends on the coupling between fiber and matrix. Between fiber and matrix. If there is so the sequential of fracture of fibers depends on the coupling. Means this is the fracture of single fiber happens, and if this sequence further proceed, so the sequence means the one by one fibers are fracturing, so the sequential fracture of fiber depends on degree of coupling. If there is no coupling, then composite will behave like a bundle of fibers. So this is the small crack propagation in the single fiber. If a large crack propagation happens in the composite, so how it will grow? So we will study the growth of large crack. growth of large cracks. So this is the composite and these are the fibers. So the crack in fiber will propagating in this direction and one big crack is propagating from the matrix to the fibers and load is applied in this direction. So failure will occur in both. In this condition, failure will occur in fiber and matrix both. So if the growth of the crack in matrix and in fiber are in a plane, so the crack front will also be the planar, and also the interfacial bonding is strong. So when interfacial bonding is strong, interfacial bonding between matrix and fiber is strong, so the crack front will be planar. Is planar, and if the bonding is not strong, weak bonding lead to a non-planar crack front. And also this also leads to crack blunting. So when fracture is non-planar, means matrix crack and fiber crack are not in the same plane. So it will the schematic will look like this is the crack in fibers, and the matrix crack in the matrix will look like this when there is a weak bonding. So the crack will also get blunted because of the non-planar growth of crack from fiber to matrix and the fiber matrix crack growth. So the fracture behavior is different in continuously reinforced composite and discontinuously reinforced composite. This is up to this point we studied the continuous reinforcement composite. are only interface bonding deals with the behavior of fracture. Means if interface bonding is strong, the crack will be planar, and if it is weak, then crack will be non-planar. And if the bonding is good with the ductile matrix, then the stress relaxation will happen by the blunting of crack. And if the matrix is brittle, then stress relaxation will be done by the debonding between the matrix and fiber. So now we will study the fracture behavior in discontinuously reinforced MMCs. Metal matrix composites. So in these discontinuously reinforced composites with the interfacial bonding, there are many factors which represents the fracture behavior. And other factors. So what are the to understand the fracture behavior of discontinuously reinforced metal matrix, first we have to study the ductile fracture in fracture behavior of the ductile materials. So the ductile fracture in metals means generally metals are only the ductile with the good strength. Ductile fracture in metals. So in the tensile loading, the subjected material will elongate and due to after some time with elongation, a necking region will start to generate. So because of the necking region, the area that is subjected to a specific load will experience higher stress levels as compared to where necking is as compared to the region where necking has not started yet. So at the necking region there will be maximum load or stress. So strain hardening during the plastic deformation also is the very known behavior of metals. Strain hardening that occur in metals. Strain hardening means what? The stress required for further deformation increased during the deformation process. So there are two competing phenomena in ductile metals. First is that the stress decrease because of reduction in area. That reduce the So this reduce the load bearing capacity of the metal, reduce load bearing ability. Second is the strain hardening. Because of the strain hardening, stress is increasing. So at the necking region, there will be an plastic instability. Means during the plastic deformation, the increase in stress due to strain hardening can be compensated by the decrease in stress. So the decrease in stress due to reduction in area at the necking region can be compensated by the increasing stress because of the strain hardening behavior of metal. So this strain hardening increases load bearing capacity. Of metal. So if we study the plastic instability at the necking, when the necking starts, so at that point where strain hardening and necking meets is called the, at that point the stress change in stress will be zero. Means the increase in stress and decrease in stress will compensate each other and the change in load will be zero. So dP is equals to 0. If we see the equation of load will be stress into multiplied by cross sectional area. A is the cross sectional area here. So if we differentiate this equation, and so dP can be written as sigma dA plus A d sigma, and if we equated this equation to 0, then we will get the d sigma by sigma equals to minus dA by A. As we know, the volume remains constant during plastic deformation. So volume is what? Area into length. So A, if the volume is length into area, that is constant. So if we dot the V naught L naught, sorry, A naught L naught equals to A L. No, if the volume is also constant. So if we differentiate this equation, that is dl A dl plus L dA will also be equal to 0. So minus dA by A will be dl by L, means change in length divided by original length. So if we write this, and this is written as the strain, and E is the true strain. So if we put this equation into the upper equation, d sigma by sigma will be d epsilon, and d sigma by d epsilon can be written as sigma. So this equation is called the plastic instability. And this is also known as the considers criteria for necking. And this plastic instability is in tensile loading. So the stress can also be written as the power law equation, K epsilon n, where n is the slope between sigma and epsilon. That can be written as d ln sigma by d ln epsilon. So this will be epsilon by sigma, d sigma by de, and as we know that the d sigma by d epsilon is can be written as sigma. So if we put in this equation, so n will be equal to epsilon. So this is at the point where strain hardening and necking is equal, and this is also known as the uniform strain before the necking, means strain up to maximum loading. So if we plot the graph between strain hardening and general stress strain curve, sigma epsilon, so this is the normal curve, sigma versus epsilon, and the strain hardening curve will start from the yielding point. This is yield point, and yield is strain. So this curve is of d sigma by d epsilon versus strain. So this at the strain at this point will call the epsilon u, which is uniform true strain. So at this point the exponent will be equal to epsilon, which is uniform strain. So this equation can also be written in the engineering stream term